Hello everyone, this is tutorial 1 for PC-TAS, the phase change thermoacoustic simulator. PC-TAS is a software developed by the Water and Energy Technologies Laboratory at the Technion, the Israel Institute of Technology. The outline of this tutorial will be as follows. We're going to start with the purpose and general description of PC-TAS, then we'll discuss installation and installation requirements, and then we're going to dive into the app itself and discuss the app outline and the basics of app operation. So, purpose and general description. PC-TAS is a simulation software for 1D acoustics, thermoacoustics, and phase change thermoacoustics. It can simulate devices such as the standing wave engine that you see right here, and the standing wave refrigerator that you see here, and it can simulate these devices both in a classical, dry mode, and in a wet mode that includes the effect of phase change. For both modes, it employs a 1D linear model, which assumes single frequency, 1D propagation of the waves, and small perturbations. For further reading about PC-TAS, we recommend this article. It includes a mathematical description of PC-TAS, as well as the code structure and some validation against experimental data. There's also a reading list for further reading about general thermoacoustics and phase change thermoacoustics. So, installation and installation requirements. PC-TAS can be installed in one of two ways, either as a MATLAB app or as a standalone desktop app. For both ways, you can download the files through our website. The link is right here. And we'll start with the MATLAB installation. This is the recommended way for anyone who has MATLAB 2020B or a later release. The installation is really simple and straightforward, and I'm going to go ahead and show it. So I'm going to go ahead and open MATLAB, and you see this file right here, PC-TAS1.mlapp install. This is the installation file that can be downloaded from our website, and you simply double click it through MATLAB, and you can click install. In my case, it's reinstalled because it is already installed, and voila, the installation is complete and the file appears right here. The application appears right here. It's under the apps tab along with the other MATLAB apps. And you just click it and you can run the application. Now this is for those who have MATLAB 2020B or later. If those who do not have MATLAB 2020B or do not have MATLAB at all, you can also install PC-TAS as a standalone desktop application. It can be installed on Windows 10. It was checked on Windows 10. It should also work on other versions of Windows and on Mac and Linux as well. For all these installations, it requires a MATLAB runtime. Now, if you do not have MATLAB runtime on your computer, you don't need to worry about it. It will be installed during the installation of PC-TAS. However, if you do have MATLAB runtime from some previous run, we recommend that you uninstall it before installing PC-TAS. We also recommend running PC-TAS only on CPUs of Intel i5 or better. It would also work on slower machines, but there might be some lags or bugs. So that was the installation, and now we're going to go ahead and look at the app itself. I'm going to go ahead and open it. You see it right here. This is the main screen of PC-TAS. It's called the drag and drop screen, and it includes all the most important parts of the application. So right here you have the new component section, where you can create a new component by dragging it into the system or sandbox. Here you have the sandbox, where you can play around with components, look at them, look at their properties without putting them in the system. And here you have the system components. These components constitute of the actual thermoacoustic system that we're simulating here. And you can also determine the system properties, such as the system name, the mean pressure, the frequency, and other properties as well. Right here at the top left, you have some things that we'll discuss in later tutorials, such as the system guesses, the system targets, and the smooth mode. You also have the run system button, which we'll use soon. So I'm going to go ahead and start by dragging a round duct from the new component section into the sandbox. I'm going to call it duct 1, and I'm going to give it a length of 0.7 meters and a diameter of 0.08, just because. And you see that the button is created right here, duct 1. I can drag it around. I can drag it into the system, back into the sandbox, and I'll drag it into the system. I can also change its properties by right-clicking it and clicking change properties. I have this little box here with all the input parameters on the left. So for instance, I can change the length from 0.7 to 0.8. I can change the diameter from 0.08 to 0.07. And note here that some of the properties are dependent. In the case of a round duct, the diameter, area, and hydraulic radius are all dependent on one another. So when I change the diameter from 0.07 to 0.08, the hydraulic radius is changed. When I change it back to 0.07, the hydraulic radius and the area are both changed. And when I change the hydraulic radius back to 0.02, the diameter is changed back to its previous value. I also want to show you that when you change the properties, I'm going to drag another duct, we call it duct 2, and I give it the default values. When you change the properties, you can also see it in the button itself. When I change it to 0.08, the button itself becomes longer. When I change the diameter to 0.04, the button becomes smaller. The size is determined based on the geometrical properties of the duct itself. So I'm gonna put these two ducts here in the system. I also know that there's a tab here called the Tables tab, where you can see all the tables together for all the components. You can also change them through here. So now I'm going to go ahead and fill in the system properties. I'm going to call the system 2 ducts, because that's what it is at the moment. I'm going to leave the mean pressure with 1 atmosphere, which was the default value. I'm going to change the frequency from 100 to 300 hertz. I can also determine the working mixture, the inert gas, and the reactive gas, which undergoes evaporation and condensation. Now, notice this little button here, the dry switch. Once I click it, the reactive gas is essentially nullified. It does not mean anything once dry switch is selected, because dry switch essentially means we're working in a classical dry mode without evaporation and condensation. I'm also going to go ahead and determine the initial conditions. These are essentially the initial conditions for the 3 parameters that we are solving for, which are the oscillating pressure, oscillating velocity, and the mean temperature. Oscillating pressure and oscillating velocities are phasors, so they have real and imaginary parts. I'm going to go ahead and give a pressure of 300 pascals, and I'm going to give a oscillating velocity, volumetric velocity to be more exact. I'm going to give it a oscillating velocity of 0.01 square meters per second. And notice that I made the pressure real and the velocity imaginary. This dictates a phase of 90 degrees between them. I'm going to leave the mean temperature with the default value. I'm going to click Run System and run the system. So once you run the system, a few things happen. First of all, notice that the right side of the boxes here is now full. The properties are filled when you run the system, and you have the oscillating pressure, oscillating velocity, mean temperature at the beginning and end of each component. Second of all, the third tab with the graphs is also filled. This is called the Graphs tab, and it includes graphs of all the properties inside the system. And you can see here the profile of the oscillating pressure, the profile of the oscillating velocity, and you can also see the temperature profile, which at the moment is simply a constant temperature of 300. This is because we do not have any components that undergo thermoacoustic conversion, so there is no reason for a temperature difference to be created. And now we're going to go ahead and do just that. We're going to add a stack. Stack is essentially the heart of any thermoacoustic system. We're going to call it stack, and we're going to leave it with the default parameters. Notice that there are some different parameters. For each component, there are different parameters that define it. And we're going to go with the default parameters, and we have stack right here. And we're going to go ahead and rerun the system. And now, when we look at the temperature profile, we see that the temperature profile is created. There's a temperature difference on the stack between the left and right side of it. And at the moment it's around 7 degrees. And if we, let's say, we increase the pressure from 300 to, let's say, 30,000 pascals and rerun the system, now we have a much larger temperature difference on the stack. So this is the thermoacoustic effect right here. Acoustic wave imposes a temperature difference on the plate stack here. I'm also gonna show you one more thing. What happens when I remove the dry switch, when I introduce phase change into the system. I'm gonna rerun the system, and I'm gonna show you two things. First of all, the temperature difference was greatly reduced. From almost 50 degrees, it was reduced to around 16 degrees. This is due to the introduction of phase change. Second of all, if we look at the graph of the mass flux right here, you see that there's a mass flux inside the stack, a positive mass flux. So essentially, our thermoacoustic wave, or our sound wave, causes a pumping of mass, or a mass flux in the positive direction from here to here. This is a phase change thermoacoustic effect. So we've seen some of the basics of the app. We see how we can play around with some parameters and rerun the system and investigate, let's say, what happens when I change the frequency. All of a sudden, instead of a wave and a half, we have around a half wavelength. This is because we changed the frequency from 300 to 100. So we can already investigate all kinds of acoustic and thermoacoustic effects with the tools we have so far. So I'm just going to show you a few more technical things in this tutorial. First of all, I'm going to show you that you can save a system. You can save it. It is saved as a mat file. I'm going to call it 2 ducts, and I'm going to overwrite the previous file that was there. And now, let's say I create a new system, and now I want to load my previous system. I just click load. I click 2 ducts, and it is all loaded. Second of all, I can also export the data. If I want to observe this data more carefully, or observe it in some other applications, in MATLAB itself, I can click export data, and I save it here on my desktop. And now, after the export is complete, I can see the folder right here, folder called 2 ducts, which was created. I can open it, and it includes all of the plots. First of all, we have the acoustic power, the pressure, all these plots that we saw before. It also includes the component data, all the data about the components, including their geometrical properties, etc., and all of the property data, the pressure profile, velocity profile, temperature profile. All of this data exists both in a Excel format and in a MATLAB format. So we can now investigate this data with any tools that we find necessary. So that's all for today. We've discussed the basics of the app, and we'll discuss more advanced features in future tutorials. So goodbye and have a nice day, everyone.